Hello everyone and welcome to Nanomedicine Lecture 2, the first lecture on biodistribution. So let's first start talking about definitions. The first definition is pharmacokinetics. Pharmacokinetics is the study of mathematical relationships between the doses and the concentration distributions of drugs at various sites in the body. A shorthand way of thinking about this is what the body does to the drug. Pharmacodynamics, on the other hand, is the study of mathematical relationships between the concentrations and the pharmacological effects of the drug in the body. Shorthand for this is what the drug does to the body. And toxicology is the study of adverse effects of chemicals on living organisms. So both pharmacokinetics and pharmacodynamics are studies of mathematical relationships. So in this section of the class, we will explore the mathematical relationships and determine equations for both pharmacokinetics and pharmacodynamics. So before we start getting into the math, let's first talk about how a drug or substance can get into the body. These are called the routes of administration. So there's 6 normal routes of administration. One is intravenous, which is directly into the vein. A second one is intraperitoneal. This is into the peritoneal cavity of the body. Intramuscular, again, exactly what it sounds like, directly into the muscle. Inhalation is breathing something into lungs. Subcutaneous is an injection under the skin, very similar to the intramuscular, but subcutaneous doesn't go as deep. And then finally, oral, which is where most of your medications are in pill form. So for the purposes of this lecture, let's talk about intravenous administration. So drugs in an intravenous administration are typically given into a peripheral vein over 1 to 2 minutes or longer by infusion. Rapid injections are used to treat, for example, epileptic seizures, acute asthma, cardiac arrhythmias. There are several advantages of this route of administration. One is that it has a rapid, quick response. The total dose is delivered to the bloodstream at one time, and so you don't have to worry about figuring out how much will be delivered and how much is left behind. The whole dose is delivered to the bloodstream. Larger doses can be given by extending the time of diffusion, so that's by using infusion or IV bags. And then finally, veins are relatively insensitive. You can use irritant drugs at higher concentrations or the vehicles, which are the solvents that are used to dissolve or solubilize the drugs, without harm. So here's an image of an intravenous drug being administered. So here's your needle, and this drug is being directly injected into the vein, into the bloodstream. With everything, there are disadvantages. One of the disadvantages is that you have to find a suitable vein. It can be difficult sometimes to find a suitable vein. It could be toxic. Because of the rapid response, toxicity can be a problem. So to overcome this, you could give the drug as an infusion and then monitor for toxicity. But you absolutely have to be sure that when you're calculating a drug for an intravenous administration, that the calculations are correct. This mode of administration also requires trained personnel. It's not something that most people can give to themselves, so you have to go to a doctor's office or to a hospital or clinic in order to get your injections. And then this is an expensive route of administration. There has to be sterility and pyrogen testing. And also, typically there's larger volumes of solvent, so it means greater cost for preparation, transport, storage, more regulations. So let's talk about the mammalian circulatory system, since we're talking about the intravenous drug route of administration. Now, I'm trusting that all of you have had some form of biology, so we're not going to go into this in any kind of depth that has been covered in any of your BME classes or any other biology classes. But just for a recap, what are the major organs of the mammalian circulatory system? I hope you remembered that the lungs and the heart are the major organs. If not, then here is your refresher. Second question, what is the main function of the mammalian circulatory system? The main function is to permit the transfer of oxygen and nutrients to tissues and also to remove waste. So for our purposes of mathematical modeling, what I want you to realize about this is that this is a closed system. And so the bloodstream flows from the heart, where the blood will go to the arteries, arterioles, and then capillaries, where the gas and nutrients will be exchanged, waste will be picked up, brought back through the capillaries, venules, up through the veins, pumped through the heart, or pumped into the lungs, and so on and so forth. And so what's important about this, again, especially for the mathematical modeling, is that it's a closed system. And these are just images, close-up images from Dr. Pierce Kotler. They're just beautiful images, again, showing at the microscopic level that it's a closed system. So from arteries to arterioles, down to capillaries, and then these capillaries end up going back into veins, and so on. Just beautiful imaging. So let's get to the math part of this. So again, the mammalian circulatory system is a closed loop system. We are going to simulate this by just drawing this gray box. And so this gray box down here with a C on it is the representation of the whole blood vessel compartment. So a single compartment. This is a one compartment model. We're only taking into account what's happening in the bloodstream. So here we are going to input a drug through an intravenous route of administration, and the clearance, so leaving the compartment, only happens by inactivation or excretion, and this happens with a rate Ke. So let's talk about the assumptions. Everything we do has assumptions. So in order for this model to hold, we have to assume that when we inject it, that it is instantaneous. This is a delta function. And that when we do inject it, it is homogeneous. So there's homogeneous mixing. There is no gradient. There is no concentration gradient. So we're modeling this as though it's a homogeneous mixing. And the initial condition is the concentration equals C0 at T equals 0. So concentration equals the initial concentration at T equals 0. Now T equals 0 doesn't mean there's any drug. T equals 0 is going to mean that delta function, that is your initial concentration, everything that was injected. So for the purpose of this, again, because it's intravenous administration and all of the drug is going to go into this compartment, that's why we can use this very simplified set of assumptions. However, when we talk about the other routes of administration, we will have to introduce volume factors to correct for the differences in the size of, or the volume of the skin versus the bloodstream, or the gut versus the bloodstream. And we'll also have to correct for the fact that not all of the drug will actually get into the bloodstream. Some will be left in the initial site. But for this one compartment model, these are our assumptions. So here I am showing you what this looks like practically. So the red are blood vessels. The green is a small molecule drug that has been fluorescently labeled. And as you can see, this is a small molecule. So it goes into the bloodstream, it goes in very rapidly, and then it very rapidly leaves. So this green here on the background is all from the drug leaving or being excreted, Ke, from the blood vessels. So an important parameter, and you'll see this parameter come up quite a bit, is T half-life. So this is the time it takes for the initial concentration to be for the concentration in the compartment to be 50% of the initial concentration. So let me say that again. This is the time it takes for the concentration in the compartment to be 50% of the initial concentration. So mathematically, T1 half is when concentration equals C0, the initial concentration, divided by 2. Simple enough. And we know from our equation equation in the previous slide, that C0 over 2 equals C0 e to the minus KET 1 half. So simplifying this, 1 half equals e to the minus KET 1 half. Taking the ln of both sides, we get ln of 1 half equals minus KET 1 half. Again, doing more algebraic simplification, ln of 1 minus ln of 2 equals minus KET 1 half. So ln of 1 equals 0, which drops out that term. So minus ln of 2 equals minus KET to 1 half. T1 half becomes ln of 2 over KE. Ln of 2 is a constant, so T1 half equals 0.693 over KE. So again, this is the blood half-life, or the T half, for the simple one compartment model. So let's go through an example. So typically you'll see these in data tables, time and concentration, or just drug amount. So here's our T1 half equals 0.693 KE. So first let's figure out what our T1 half is. So why don't you go ahead and pause the lecture and try to figure out what T1 half is. Alright, so here's how I would solve it. Well, first, this is a really easy example. So just by knowing the definition of T1 half, you can go where the concentration is 50% and you know that the time is 10 minutes. But for more complex examples, what you would do is you would plot the time on the x-axis, drug concentration on the y-axis, and then you can solve the equation, the exponential equation. So we know now that the T1 half is 10 minutes, and then from there we can go back and we can figure out what KE is. So by doing that, KE equals 0.693 T1 half, so KE equals, in this example, 0.0693. So knowing T1 half, we can get KE, and knowing KE, we can get T1 half. So another thing with this is that one of the parameters that determines blood half-life is going to be size. There are other parameters, but for right now, let's just focus on size. So something that's small, like the small molecule example that I've already shown you, has a very short vascular half-life. Very short. It goes into the bloodstream and then it quickly goes out. Something, though, that's a nanoparticle, something that's bigger, will stay in the bloodstream much longer. And so this example is showing a fluorescently labeled nanoparticle that still, after 4 hours post-injection into the blood vessels, is still in those blood vessels. And so it has a very long T1 half. So again, let's pause the talk and let's use this part of the lecture to try to answer questions 1A and 1B. I hope you actually paused the talk and tried to answer this question, and I'm going to show you in the next few slides how I would go about answering this question. So large fluorescent macromolecules are used to image vasculature. Their large size and absence of targeting motif allow them to stay in the bloodstream for extended periods of time. One such imaging agent is angiotensin 680. In a typical experiment, a 150 microliter bolus of angiotensin 680 is injected intravenously at time t equals 0. To obtain pharmacokinetic information, tiny amounts, negligible volume, of urine were collected at different time points and the AS680 concentration was determined. In this situation, the concentration of AS680 in the blood decreases solely due to urinary excretion. The urine data is presented in the table below. The blood volume of a mouse is 2 milliliters and the 150 microliter bolus can be considered negligible. So what model should be used to determine the AS680 concentration profile? Well, based on the fact that this is an intravenous route of administration and we're trying to measure what's happening in the bloodstream, and the blood concentration decreases solely to urinary excretion, this can be modeled as a one-compartment model. So from there, the B part, write the equation for the concentration of AS680 in the blood as a function of time. Include the numerical value of C0 and Ke in your equation. So here's how I would go about writing or doing this. So the first thing that we have to do is determine C0. So to determine C0, you have to consider the amount of AS680 injected into the mouse. So CAS680 equals 200 micromole per milliliter, and we injected 150 microliters. So the amount injected equals 200 micromolar divided by 0.150 milliliters. So again, make sure you pay attention to your conversion factors. 150 microliters is 0.150 milliliters. So this is going to equal 30 micromoles. I told you in the question that the total volume of the mouse blood is 2 milliliters, and we did a bolus injection. So this is not an infusion, everything went in at once. And I also allowed you to assume the injection volume is negligible. Not always the case, but in this case, to simplify things. So C0 equals 30 micromolar over 2 milliliters. So the C0, the initial concentration, equals 15 micromoles per milliliter. Moving on from that, we now have to calculate Ke. In this case, we don't have blood data, we have urine data. So to start out, what I would do is I always sketch out the data. And from sketching out the data, it looks like the inverse of compartment 1 concentration, so plasma blood concentration. And this makes sense. I told you in the problem that the elimination was solely due to urine excretion. So due to mass balance, concentration in the urine must equal the inverse of plasma concentration. So if anything's showing up in the urine, it had to have come from the plasma compartment, so from that blood compartment. And so that's how we're going to use the urine data to find the plasma concentration. So C urine should equal C0 minus C plasma. C urine equals C0 minus C0e to the minus KET. And we know how to find Ke if given an exponential function by taking the ln of C and calculating the linear regression. So that's exactly what we're going to do. We are going to use the data, the C urine data, which is on this column. Here's our C urine data. We're going to plug this into the equation and then take the linear regression to find Ke. So C urine minus C0 over minus C0 equals e to the minus KET. Taking the ln of the left side, or taking the ln of this left side of the equation, we complete the new table, and from there we get the slope of the fitted line. Again, the linear line is 0.0009 Ke. So C plasma equals 15 micromole per milliliter. We calculated that from before. That's C0 e to the minus 0.0009 T. And we found C0 and Ke given the data. So I know this was a little bit more complicated, and I threw kind of a monkey wrench in there by adding the urine data instead of the plasma. But again, it's very important to understand all of these concepts and be able to apply them. We will, in your discussion sessions, Monday or Wednesday, we will be doing several worksheets where we, again, use these concepts and get really familiar with being able to take a problem and being able to solve it using pharmacokinetic analysis. Another parameter that's very important, switching gears a little bit, is area under the curve. Now, area under the curve, when you say this to a mathematician or an engineer, is automatically means integration. And that's not where this becomes a problem. What becomes a problem is in pharmacokinetics, we don't say, oh, what's the area under the curve? We're actually looking for something different. Area under the curve means something biologically. Area under the curve means it's the cumulative exposure of a compartment to a specific drug. And so what we do is we integrate from 0 to infinity the concentration in that compartment. And so the concentration of the compartment, we already know that mass balance equation, that's C0 e to the minus KET. And so area under the curve, we integrate equals C0 over KE. So for the simple one compartment model, the area under the curve, or the cumulative exposure, equals 1.443 C0T to the 1/2. And finally, the last really important term for this is body clearance, which is the rate of drug elimination in the body relative to the drug's plasma concentration. Very important, relative to the drug's plasma concentration. Very important term. So in a one compartment model, plasma concentration is the same as the concentration in the blood compartment. So it's the same in the central compartment. So CLB, clearance in the blood, equals volume KEC over C equals volume KE, or CLB equals 0.693 V over T1/2. Very simple. So let's go ahead, pause the talk, pause the lecture, and try to solve the C portion of the question I asked you before. So using the same data and using what you know from solving part B, try to solve part C. So again, hopefully you paused the lecture and actually tried to solve it. And here I will again walk you through my thoughts and how I would solve this question. So the question is, suppose AS680 was toxic to the red blood cells circulating in the blood. Once total AS680 plasma exposure reaches a toxic value, 2.5 millimole per milliliter, red blood cells lyse. Using your concentration equation from part B, how many minutes after injection will the red blood cells lyse? So what are we going to do to be able to answer this question? Well, again, this is the area under the curve, and that's exactly how it would be asked. So again, area under the curve really measures total exposure of a drug in the compartment. So area under the curve equals the integral of 0 to infinity of the concentration in the plasma, which equals the integral of 0 to infinity C0 e to the minus KE dt. So in this case, we know a total exposure before toxicity sets in. And in this case, we are trying to figure out what T is. So we already know what the value for area under the curve is, and we're trying to solve for T. So again, pay attention to your conversion units. I gave it to you as 2.5 millimole per milliliter, and we solved all of our concentrations in micromole per milliliter. So make sure that you've converted that properly. So 2,500 micromole per milliliter equals the integral from 0 to T, C0 e to the minus KET. So just pulling out the constant, 2,500 equals C0, integral 0 to T, e to the minus KET. Again, integrating that, 2,500 equals C0 minus 1 KEE to the minus KET from 0 to T. 2,500 equals minus C0 KE, e to the minus KET, minus e to the minus KE0. So minus e to the minus, or e to the minus KE0 can simplify to 1. So it simplifies the equation to 2,500 equals minus C0 KE, e to the minus KET minus 1. Doing some algebraic rearranging, 2,500 KE divided by minus C0 plus 1 equals e to the minus KET. More simplification by taking the ln of both sides. Ln of 2,500 KE over minus C0 plus 1 equals ln of e to the minus KET. Minus 0.163, so here we know what C0 is. That's the 15, we know what C0 is, so by plugging that in and solving, that whole left side of the equation simplifies down to minus 0.163 equals minus KET, and then solving for t equals 180.6 minutes. So 180.6 minutes after injection, all of this mouse's red blood cells will lyse. So let's go through and do a lecture 1 and lecture 2 recap. So in lecture 1, we talked about nanomedicine techniques, materials, and equipment. We talked about the nanoscale. What is the nanoscale? Examples of nanoscale. And that the high surface area to volume ratios actually modulate the properties, and that's why nano is so important. We will talk further about EPR effect, or enhanced permeability and retention, also molecular interactions. In this lecture, we defined pharmacokinetics and pharmacodynamics. We talked about routes of administration, focusing on intravenous routes of administration. We also talked about the intravenous advantages and disadvantages. And then in lecture 1, we talked about applications of nanomedicine, drug and gene delivery, tissue engineering, tumor detection, imaging contrast, and also some on the horizon applications, the nanosponge and also nanorobotics.